Okay, I think I'm going to get started. Um, Pretty important lesson today. It might be new material for the majority of you. Um, we're going to be discussing a whole bunch of stuff actually, but based on the angles and standard position. I want to start by talking about these two special triangles, which I'm actually going to show you a trick for on the next slide. But there are angles that we use quite a bit in trigonometry. And those angles are the 30, 45, and 60 degree angles, along with 0 and 90 degrees. But with 0 and 90, I'll show you how to do that in a second. But the 30, 45, and 60 degree angles, these are two triangles that a lot of teachers in textbooks will get students to memorize to help them remember what is the cosine of 30, 45, and 60, and what is the sine of 30, 45, and 60, but not as decimals, as fractions. We want to have some fairly accurate values sometimes when we're calculating with trigonometry. We don't want to use the decimal values that you would get on your calculator. We'd want to use the fractional values for sine, cos of these three angles. So these two special triangles are supposed to help students remember those values. I actually don't use them. I use the technique I'm going to use on the next slide, but I do want to show it to you because it is commonly used. So we're going to concentrate on the first triangle here with the 30 degrees and 60 degrees. Now what's nice about this triangle is it actually covers both of those special angles because to add up to 180, if you designate one angle as being 60, the other one's obviously going to be 30, right? So the first thing we need to do is calculate the length of this side. So using the Pythagorean theorem, how quickly could you calculate the length of this side? Well, we know that a squared plus b squared equals c squared. We know that the c value is 2 here. Let's call this b. So we'd be looking for the a value. Now, to speed things up here, it'd be a squared plus b squared equals c squared, which means that a is equal to c squared minus b squared square rooted. So quickly putting those numbers in, we get 2 squared, which is 4, minus 1 squared, which is 1, and this gives root 3 as that length. All right? So what I want to do now is I want to talk about the cosine and the sine of both 30 degrees and 60 degrees. So let's actually start with 30 degrees. What would be the cosine of 30 degrees? Well, the cosine is the adjacent over the hypotenuse. The adjacent side is this root 3. The hypotenuse is 2. Now, if you do cosine 30 on your calculators, you're going to get 0.8660, and it's a irrational number. It continues forever. But we can now, from this point on, if we need a perfect answer for the cosine of 30, we can use root 3 over 2 for that value. What would be the sine of 30? Well, the sine of 30 is the opposite over the hypotenuse, and a lot of you already knew that the sine of 30 was 0.5 the other day, but you know, it's still, to keep the format the same, we could use 1/2 as our fraction, which is given to us by this special triangle. And even though the textbook that we have doesn't go into the tangent values too often, we can actually do tangent. Tangent is opposite over adjacent, which would be 1 over root 3. And we're going to have a bit of an issue with tangent. I think this is the reason why it's not in your textbook. And this is one of the exceptions to the rules to rationals. Sorry, not rationals, radicals that we talked about earlier on in the course. You're technically not supposed to have a radical on the bottom of a fraction. But for some reason in trigonometry, they often will allow it. But it shouldn't be. It should follow the same format as everything else. So what we would do in this case is we would rationalize the denominator by multiplying both the top and the bottom by root 3. And for our tangent of 30 degrees, we'd end up with root 3 over 3 instead. Okay? So you can actually find all of the sine and cosine values and the tangent value for 30 degrees in fractional form, which is better than decimal form because it's a perfect value, using that first special triangle. And I'm going to summarize these in a table in a second. We can do the exact same thing for the other special triangle. Now this is a special triangle because of multiple reasons. First of all, if this angle is 45, that means this angle is also 45, which makes this immediately an isosceles triangle. And we're going to label the two sides as 1 in size, which means we have to calculate the hypotenuse again. Sorry, the unknown side again. In this case, it's the hypotenuse. So if we calculate c would be the square root of a squared plus b squared, but in this case it's just 1 squared plus 1 squared, which becomes the square root of 2. So we now know that c is equal to the square root of 2 on this triangle. What would the cosine of 45 be then? Well, the cosine is the adjacent over the hypotenuse, which would be 1 over root 2. And this is another case where you will often see in textbooks, they will break the rule for radicals on the bottom of the fraction, and they will actually just leave it as 1 over root 2. But I'm going to rewrite it in its rationalized form. So I'm going to multiply by root 2, and I'm running out of room on the side of the screen there, that's why it's written really small, but I'm going to multiply the top and the bottom by root 2, and that's going to give us root 2 over 2 as the cosine of 45 degrees. I believe the number is 0.717 or something like that. I can't remember off the top of my head, but this is a much, much cleaner representation of the cosine of 45 degrees. If we do the same thing for sine 45, well, what's interesting about this triangle is that because it's an isosceles triangle, the opposite over the hypotenuse and the adjacent over the hypotenuse give us the same thing. So we'd end up with root 2 over 2 again. If we wanted to do the tangent of 45, we can do that as well. It's opposite over adjacent, which is 1 over 1. So the tangent of 45 is just 1. So if we summarize that in our table here, what is the sine and cosine of 30? So the sine is 1/2. The cosine is root 3 over 2. What is the sine and cosine of 45? It's root 2 over 2 for both. And then for 60, sorry, it's actually just the opposite of the 30 degree one. I haven't done the 60 degree one yet because I wanted to do these two first. But if we do the sine of 60, the sine of 60 is the opposite over the hypotenuse. Well, the opposite is root 3 over 2, but root 3 over 2 is the cosine of 30. So these two for 60 just are the opposite of what the cosine values are what the 30 degree angle values are for sine and cosine. So it would be root 3 over 2 and 1/2, like so. So those are how the special triangles work, but I have, in my opinion, a better way of remembering all those values. And that's going to lead us into the second part of the lesson today, which is actually going to cover multiple different things here, but I'm going to start by showing you the trick that I like to use for remembering what is the cosine and sine values of 30, 45 degrees, and 60. So the first thing I want you to notice is this is 30 degrees, this is 45 degrees, and this is 60 degrees. Okay? Now here's the trick that I learned to help me remember what the cosine and the sine values are of those three angles. Now, I want you to remember that when we were doing the angles in standard position the last time, I mentioned how the coordinates of the points on the where the radius intersects the circle are the cosine and sine values. And I'll show you with the right angle triangle here. If I drop a line down as a right angle triangle, the cosine of 30 would be the x value of that triangle because it's adjacent over hypotenuse. Now remember, the hypotenuse is a 1 for the radius 1 circle. Okay, so the cosine of 30 is just the x value, and the sine of 30 is the opposite over the hypotenuse, which is just the y value. So that means the coordinates of this point right here are the cosine of the angle, sorry about that, and the sine of the angle. So the coordinates of those points all the way up are just the cosine of the angle and the sine of the angle. Now watch what we can do. If we start at the top of the circle, if I write the number 1, 2, and 3, and then I go back up the circle going 1, 2, and 3. And then if I divide everything by 2, so you'd have to remember this pattern, okay? So starting with the 60-degree angle, you go 1, 2, 3, 1, 2, 3, divide everything by 2, and the last step is to square root every number that's worth square rooting as a numerator of those fractions. So the square root of 1 is just 1, so there's no point in square rooting that one. But if I square root the 3, that there's actually a value to that. Square root the 2's, and then square root the 3 here. And what we end up with are the sine and cosine values the cosine and sine values. I should say it in order. So the first column would be your cosine values of each one of those angles, and the second column would be the sine value of all of those angles. And for me, this is much easier to remember than those special triangles. But if you look, cosine is 1/2, cosine of 60, sorry, is 1/2. Sine of 60 is root 3 over 2. If we go back to the table that I just wrote here, cosine of 60 is 1/2, and the sine of 60 is root 3 over 2. I should have put these in the same order that I was going to do them on the separate slide. I'm sorry about that. I didn't even think of it. I don't know. I find sine and cos slides easier off the tongue than cos and sine, but the cosine is the first column and the sine is the second column. So we really, really should say cosine first and then sine second when we're listing those things. And the tangent is an interesting one because the tangent is the opposite over the adjacent. There is another alternative to calculating the tangent. The tangent, let me just use this color here. The tangent of an angle is actually equal to the sine of the angle, divided by the cosine of the angle. Which I think I'll leave as a proof for another day because that's actually called one of the trig identities. So I think I'll wait before I show you the actual proof of that. But if you take all the sine values and divide them by all the cosine values, it actually will give you the tangent value of the angle. So these three angles give you, with this magic circle, give you the cosine and sine of those three angles quite easily in fraction form. Now, as we had done last time, if I mirror those lines onto this side, I'm going to try to get it as accurate as possible here. Not only do I know the sine, cosine, and tangent of 30, 45, and 60 degrees, but I also know, and this is where this circle gets a little bit messy, but if I go from here all the way to this angle, well, what is that angle? Well, that angle is 180 minus 60, which is 120 degrees. Well, I actually know the coordinates of that point as well, because it's just a mirror image of these points on this side. So now if I asked you, what is the cosine of 120? As long as you realize that 120 is the supplementary angle to 160, you can say, okay, well, it's the same as these two top ones here. So I would go 1, 2, 3, 1, 2, 3, and I'd realize that the 60 is the 1 and the 3 at the top. So I do divided by 2 and then square root the top numbers. So that's how I quickly figure out what the cosine and the sine of 120 would be without the need of a calculator. But I have to put a negative in front of the 1/2 because I'm on the left-hand side of the y-axis. So all of the x values, which is the negative 1/2, are negative on this side. So without changing the color of each one, that means that the next angle, so I'm just going to put a dotted line going all the way to that one. So the next angle is 180 minus 45, which is 135 degrees. So 135 degrees would have the exact same coordinates as 45 degrees. Except that the x value would be negative. And then the next one, which is 180 minus 30, which is 150 degrees. So maybe I'll just, I don't know where to put that without making this too messy. It would be a green one. Maybe I can just do this. So that's 150 degrees. That would be root 3 over 2, but then negative root 3 over 2 and 1/2. So I now know 30, 45, and 60 fractional versions of the cosine and the sine of each one of those. And I know 120, 135, and 150 as well. Now, if I was to do it down here, and just to speed things up, I'm just going to put the 3 lines here, okay? If I was to do it down here, we'd have 180 plus 30, which is 210 degrees. We'd have 180, plus 45, which would be 225. And we'd have 180 plus 60, which is 240, if I'm not mistaken. And I now know the values of those angles as well. They're just the exact same numbers as the ones over here, but both of them are negative. So it'd be negative 1/2, negative root 3 over 2, negative root 2 over 2, negative root 2 over 2, and wait a second, I'm making a mistake there. Sorry about that. I made a mistake there. So the 210 is mirrored from the 30-degree angle, which is root 3 over 2 and 1/2. Both of them are negative. And then this one here is mirrored with the 60-degree one, which is 1/2 and root 3 over 2. In that order, both of them are negative. And I could continue to this one as well. And the only thing that would be different with this one is the signs. So in this case, we'd have a positive cosine and negative sine. Positive cosine, negative sine, positive cosine, negative sine. And the reason I wanted to do all of that is to explain what did I mean by the ASTC rule. Now, the ASTC rule is supposed to be a rule that's supposed to help students remember which ones are positive and which ones are negative based on which quadrant you're in. So if we list the quadrants, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. In quadrant 1, which ones are positive? Cos, sine, or tan? Well, in quadrant 1, all of them are positive. So you put an A there because cosine is positive all the way down, sine is positive all the way down, and if tangent is equal to sine over cos, tangent is also positive. Now, which ones are positive in the second quadrant? Well, that would be only the sine values. The sine values are the second fraction in these coordinates. All of those are positive. Cosine is negative, so it's not positive. And because tangent is the division of both of them, tangent would also be negative, so it's not positive. So only the sine values are positive. The next one down here is the t. Well, t stands for tangent. The only thing that's positive is the tangent. Why? Because cosine is negative, sine is negative. But if I divide the two to get the tangent, a negative divided by a negative gives a positive. So only the tangent is positive down here. And over here, in this quadrant, which is quadrant 4, is the c from the ASTC rule, because only the first fractions are positive, the second fractions are negative, and if I divide the two, that's going to be negative as well, which means tangent is going to be negative. So cosine is the only one that's positive. So this, now you're starting to see why I like to call this the magic circle, because of everything that it can show us. It can show us so many things. It can show us the, and I've already explained this, the cosine and the sine of all of those angles. And we also know which quadrant contains which ones that are positive. Now, the ASTC rule, I don't know if textbooks have started to do this as well. I think I have seen it like this. They used to call this the cast rule. Now, I don't like calling it the cast rule because, and it does spell the word cast if you start from the fourth quadrant going counterclockwise, but we don't measure the angles starting from the fourth quadrant. We always measure them from the first quadrant. So I didn't want to call it the cast rule because I was messing up some students thinking, oh, well, the special, all the normal angles are down here. No, your starting angles are here. Now, the fact that these are your starting angles is important because those are actually called your related acute angles. So for instance, if I asked you, what is the related acute angle to 135? Well, the related acute angle to 135 is 180 minus 135, which is 45 degrees. So the words related acute angle mean which angle in the first quadrant can we use to mirror to find the angle that we're working with. So what is the related acute angle to 210? 210 is mirrored by 30 degrees, and we can find that by subtracting 180 from 210. And you can go all the way around the circle and find your related acute angle that way, which I actually have, I think, a slide coming up that shows examples of that. I'm going to pause there for a second. I know that that's a lot of information. Are there any questions or something you'd like me to go over a second time just to make sure you understand it? Of course, with more practice, this will become easier as well. I'm not seeing any questions in chat. If I can summarize, the most important thing is being able to generate these three coordinates here in the first quadrant. If you use the 1, 2, 3, 1, 2, 3 trick, divide everything by 2, square root all the top numbers, that is going to hopefully allow you to remember, okay, well, those are the cosine and sine values of those three angles. What are the cosine and sine values of all of the other angles that are related to those ones? Okay. Now, there's a couple of other things I wanted to talk about before I move away from this slide. What would be the coordinate of this point right here, chat? So let me give you a hint. This is a radius 1 circle. This is a radius 1 circle. What would be the coordinate of that point? What is the x and y coordinate of that point? Okay, seems like I have you stumped because I'm not getting the correct answer. If I look at this as being, oh, there it is. There's the correct answer. If this is a radius 1 circle, I'm going 1 out and 0 up. So the coordinates of that point are 1 and 0. Well, what does that mean when it comes to the cosine and the sine? Well, what is the angle that gives me this horizontal line? That would be the cosine of 0 and the sine of 0. So if you can visualize this magic circle in your head, you now also know the coordinates for that point, and you can tell me what the cosine and sine of 0 are without having to type it into your calculator. Now, what would be the coordinate of this point up here? So that one's 0, 1. So that means you've got the cosine of 90, which is 0, and the sine of 90, which is 1. So you now also know the cosine and sine of 90. And if I go all the way around the circle, you should be able to tell me what the cosine and sine of 180 is. You should be able to tell me the cosine and sine of 270 as well. And we now know 4 extra angles, the cosine and sine value of them with this magic circle. So it is extremely powerful as a tool to be able to figure that all out without needing a calculator. And I'll show you in a second how I do it on paper when I'm doing questions that I have to figure out. But there's one more thing I want to discuss, and that's negative angles. It is possible to have negative angles. Negative angles go this way. So if I ask you what is the angle, what is the cosine of negative 60 degrees? Well, that just means go counterclockwise 60 degrees. Okay, so we're going to be talking about both positive angles and negative angles in an upcoming assignment, and probably today if we have time. So you need to know that you're measuring negative angles counterclockwise. Okay? So one thing that I want to just briefly discuss, because this is going to come into play a little bit later on, and it actually did come into play a little bit when we were doing the cosine law proof in the last lesson. We're going to start seeing trig identities very soon. Trig identities are ways of taking a more complex trigonometric expression and make it a little bit simpler. And I briefly discussed this yesterday, but I'm going to go a little bit more in detail today. We didn't do the sine 180 minus theta one, so we're going to start with that one. Why is sine 180 minus theta equal to sine theta? Well, it's very simple. We already saw that. Sine theta is the vertical line from the point on the circle down to the x-axis. So the corresponding one would be over here, right? Well, what is the angle going up to this line? It's 180 minus 30. The height of the triangle equals the height of the triangle for 30 degrees. And same thing for the height of the triangle at 60, same thing for the height, at 45, same thing for the height of the triangle at 60. In fact, the sine value of any angle in the first quadrant is going to equal the mirrored sine value in the second quadrant. So that means the sine of 180 minus theta is equal to sine theta, because the heights of those two are the same. Now, why is the cosine a little bit different? Well, that's because the cosine value is the horizontal length. Sorry about that. The cosine value is the horizontal length of the triangle. So 180 minus theta would be this triangle here. And the side length, the horizontal side length, is in the negative side of the x values. So the cosine lengths are the same for those two angles, but one of them is negative and one of them is positive. So that gives us this identity of 180, cosine of 180 minus theta is equal to the negative of cos theta, because this is the second quadrant's value, and this is the value that it would become if I dropped it from the second quadrant. I didn't explain that correctly. The cosine of 180 minus theta is equal to minus cosine theta because of that switchover in quadrants. I guess that's what I'm trying to say. Now, if you really wanted to know if you understood what I just said, what if I asked you, what is the sine of 180 plus theta? What quadrant am I in if I do a sine of 180 plus theta? Now, I want you to understand that theta is always a related acute angle. And if we just talk about the 30, 45, and 60 for now, it could be any angle in the first quadrant. But if we just talk about the three special angles, what would I be asking you if I asked you to find the sine of 180 plus theta? And somebody's already answered it in chat. I'm asking you to find the sine value in the third quadrant down here. Well, the sine value is the height of the triangle in the third quadrant, and we know that the heights in the third quadrant are all negative. So that means if I take the negative of the sine of the related acute angle in the first quadrant, I'm going to get the same answer as if I do the sine of 180 plus theta. And if I do cosine of 180 plus theta, what would that be? And basically I'm asking you, is it positive cos theta or is it negative cos theta? And I hope you can see that it would be negative cos theta as well, because you'd still be in the third quadrant and you're doing the horizontal distance. Now, this is what I meant in my blurb on the Google Classroom. Actually, I'm not sure if I said it. I was going to say that this lesson may take 2 days, because I've just spent, I don't know what, 25 minutes just on this one slide because of how packed full of information it is. So I'm not sure how much further I want to go. I think I want to go one more slide, but I may keep the rest of this lesson for tomorrow, because this is a lot of information to try to process, especially if you've never seen it before. Okay. Now, I promised you I'd show you what I like to do if I'm given a question that is dealing with, let's say I haven't done trigonometry in a while, and they ask me to do the cosine of, let's see here. What if they ask me to do the cosine of 300? Okay. So here's what I do. The first thing I'm going to do is I'm going to say, what is the related acute angle? I'll just write out the instructions here so that when you look back at the note, you'll be able to see what I was asking you to do. So I've got to figure out what the related acute angle is. So very quickly, I'm going to draw out my magic circle, and I'm going to just give myself a sketch of where 300 would be. Now 300 is in the fourth quadrant. Now how do I know that so quickly? Well, I know that so quickly because this angle is 270 and this angle would be 360 or 0 depending on how you're measuring it. So 300 is in there somewhere, okay? How far away is 300 from 360? Well, 300 is 60 away from 360. So if I do 360 minus 300, that's going to give me my related acute angle. And I'd like to leave it up to you to figure out how mathematically you determine that. I don't want to show you all the answers because the process of thinking about it is going to help you understand it. But anyway, that is my related acute angle. So now I know that I have to do the cosine of 60 and I'm in the fourth quadrant. So is the cosine positive or negative in the fourth quadrant? Well, I already know that the answer is positive because it's a horizontal distance and all the x values are positive in the first and fourth quadrant. Or I can use the ASTC rule. And the ASTC rule says that the cosine is positive in the fourth quadrant. Okay? ASTC. All right? So I know that my answer is going to be positive, and it's going to be the same answer, therefore, as cosine of 60. So here's what I do to remember which one cosine is 60. And I'm going to admit that my memory is not great, okay? But I don't draw out the entire magic circle. I just go 30, 45, 60, 1, 2, 3, 1, 2, 3. And I already know that the answer for the cosine of 60 is this fraction. So what is that fraction? Remember, you divide everything by 2. And then square root all the square rootable values at the top. Well, they're all square rootable, but the square root of 1 is just 1. So I now know that that answer is 1/2. And if you get good at this, you can do that faster than you can on a calculator. Because I just count 1, 2, 3, 1, 2, 3, figure out which one I'm at, and then do all that division stuff as I'm writing down the answer. So you can get quicker to do this than with a calculator if you get used to it. Okay. Let's look at these examples here now. And now I'm moving away from the special angles. Now I want you to clearly see, what do I mean by solve for theta when theta is between 0 and 360? The problem is there is no longer just one answer for these. If I hadn't said between 0 and 360, I'd be just looking for one answer. But because I'm saying from 0 to 360, we as people learning mathematics have to understand what that means. That means on the magic circle, what two angles will give me that answer as a ratio? Now, for the first one, should be pretty easy. Let's just arc cosine and see what happens. So what is the arc cosine of 0.6742? So let me call up my calculator here. 0.6742 arc cos. That gives me 47.6 degrees, so let's round it off to 48 degrees. Okay? Great. However, 48 degrees is here. The cosine is the x value. What other angle would also give me that value? Well, the cosine is positive in the all quadrant as well as the C quadrant. So that means I have to mirror this angle down here. What's the quickest way of calculating that angle? Well, if I go all the way around to 360 and subtract that mirrored angle, it's going to give me my answer. So to find the other angle, I'm going to do 360 minus 48. And somebody's already written the answer as 312 degrees. So my answer to this first question is 48 degrees and 312 degrees. And I just realized that I'm kind of giving away the that question that I said on the previous slide that said, you know, how do you calculate your related acute angles? Well, I'm kind of giving it away here. What about the sine of 0.1568 negative? Well, what happens when I arc sine negative 0.568? Well, let's see on a calculator. Let me just clear all this information out here. If I arc sine, so 0.568, this calculator is one of the older styles that I have to put in some of the values afterwards. So, oops, second sine. That gives me negative 35 degrees. What? So let me transition back to my smartboard here. Okay, I hope everybody can still hear me. So that gives me negative 35 degrees. Well, where is negative 35 degrees? Negative 35 degrees, following what I just explained about negative angles, is down here somewhere. But the problem is, that one's not even between 0 and 360. I have to have the angles between 0 and 360. Why is the calculator giving us negative 35 degrees? Because the calculator is programmed to give you the closest angle to the first quadrant, whether it be positive or negative, okay? Which I don't understand fully, but that's the way the calculators are programmed. So we've actually got to find, actually in this case, there might only be one angle that gets us to there that's positive, right? So we actually only have one angle that's between 0 and 35 degrees. Oh, wait a second. Yes, I'm forgetting that there's another quadrant that we can go into as well. My mistake. What other quadrant is the sine negative in? The sine's also negative here. Sorry, I got confused there for a second. So there are two angles between 0 and 360. There's this angle here and this angle here, which will give us a sine value that's negative. Now, how did I know it was both of those quadrants? And this is where I don't like, again, the ASTC rule very much, because the ASTC rule just tells you which quadrants are positive. So now your brain has to say, okay, well, I'm looking for quadrants that are not positive. So if the sine is positive here and here, that means it's not positive here and here. I would much rather think of this as horizontal distances for the cosine and vertical distances for the sine. Okay? So how do we figure out those angles? Well, it would be 180 plus 35. And it would be 360 minus 35. And those would give you your two angles. So I believe somebody's already told them in chat, so it would be 325 and 215 for me, I believe, the way I rounded it. Okay? And that's how you could figure that out. And I needed my calculator to do the first arc sine, but that's not the correct answer, right? The negative 35 is what my calculator gave me, but that doesn't fall within the range of the answers that I had asked for, so therefore I have to do a little bit of math to find the correct answers. So it can be very tricky, but I'm hoping you're seeing that the magic circle can actually make things a lot easier to figure out. And folks, like I kind of mentioned already, this is a very heavy lesson, and I think I'm going to finish there for today. I am going to be posting some homework questions. Now, your textbook does not go from 0 to 360 for these questions. It goes from 0 to 180, meaning it only covers the first and second quadrant. I guess it thought that it might be a little bit too difficult to do the third and fourth quadrant at the same time. So you're not going to see any questions that go into the third and fourth quadrant. Not from your textbook, anyway. I'm pushing you further than your textbook, But I'm going to do that on the assignment that you're probably going to get tomorrow, and it's going to go into Friday as well. But I'm going to stop the lesson today. I'm going to give you some homework questions in your textbook. I'm just going to stop recording here for the lesson. So goodbye for the recording.